Okay, let's think about how to compute PageRank itself. And to do that, we're going to have to think about what it means to be in a random walk. So let's introduce a probability vector, row vector, x, and x will tell us where the random walk is at any point. So let's start with a simple version of x. Let's say that we're either in a state or we're not. So let's say there's n possible nodes on the web, or states in our search, in our walk, and the vector is 0, 0, 0, 0, and then a 1 at position I, and then a lot of other zeros, means that we're in state I. So if the 1 means we're in state I, and the 0 means we're not in any of the other states. We're not in state 1 or state n or so on. And we can generalize this to say that, instead of using 1s and 0s, we can have these x's be probabilities. And so we can say that this vector probabilities tells us what the probability is of the walk being in state I at any point. And of course, these i's have to sum to 1 because they're a probability. So instead of 0s and 1s, we can have 0.3 and 0.3 and so on, as long as everything sums to 1. And that's going to be our row vector that tells us where we are in the walk. So if our probability vector is a particular vector x and it has a certain set of values, the current state of the walk, where we are, distributed over possible places we could be, what is it at the next step? If at the next step of our walk, what is it? And it turns out the transition matrix P is exactly designed to tell us that. Row I of that transition matrix tells us where we go from state I. So if we're in state x right now, that's the distribution over places we could be, then the next state is distributed by xp. So we just multiply x by the transition probability matrix P, and that will tell us what our next probability distribution over states is. Now, a couple quick definitions. A Markov chain is ergodic if you have a path from any state to any other, and if for any start state after a finite transient time t0, the probability of being in any state at a fixed time t is non-zero. So an even odd network where after a particular time t, we don't have a non-zero probability of being, let's say, at the even states if we're in an odd numbered time period. This is not an ergodic network. Now, it turns out that for an ergodic Markov chain, there is a unique long-term visit rate for each state. So there's a steady state probability distribution, pi, so pi 1 through pi n. That's the probability for each state. Probability pi 1 is the probability of long-term ending up in state 1. Pi n is the probability of long-term ending up in state n. And over a long-term period, we'll visit each state in proportion to this rate pi. So pi sub I is going to turn out to be the page rank of state I. And it turns out it doesn't matter where we start. So let's look at an intuition. The steady state is a vector of probabilities, where pi sub I is the probability we're in state I. So here's a little two-node graph. And here, pi sub 1 is a quarter. So you can sort of intuitively see that the probability from node 2 of going to node 1 is a quarter, and the probability if you're in node 1 of staying in node 1 is a quarter. So over the long run, the probability that we're going to end up in node 1 is a quarter. And whereas for node 2, we have both a loop-back probability of being of 3/4 and a probability of going from state 1 for 3/4. So here the long-term visit rate is going to be 3/4. All right, so that's good for an intuition. But how do we compute this in a general case? So again, we have pi, the row vector of steady state probabilities. And here's a fact: if our current position is described by pi, then the next step is distributed as pi p, because p is the transition probability matrix. So if we're at distribution over states now is described by pi, then by definition the next state, the next step in our random walk, is distributed as pi times the transition probability matrix. Okay? But pi is the steady state. So by definition, pi is pi times p. We know that the next step from the steady state brings us back to the steady state. And if we solve this equation, what we get is pi. So pi is in fact the left eigenvector for the transition probability matrix P. And transition probability matrices always have largest eigenvalue 1. So this is going to be the principal eigenvector of P. A simple way to compute pi is the power iteration method. And let's see how that goes. recall that the definition of a steady state is that wherever we start, we're going to end up in this steady state. So we could start anywhere. Let's start with the distribution with probability 1 being in state 1 and probability 0 being in every other state. And then we multiply by our transition probability matrix P. So after one step, we're at xp. After two steps, we're at xp squared. And then at xp cubed and so on. So eventually means for some large k, xp to the k, we're at pi. And so what we're going to do to estimate pi is just multiply x by increasing powers of p until the product looks stable, and we'll call that pi. So let's look at an example of power iteration. We'll use the transition probability matrix we saw earlier with a 0.5 teleportation probability. And let's say the surfer starts in state 1. That means that the state of the random walk is the vector x with a 1 being in state 1, and a 0 being in state 2, and a 0 being in state 3, because there's only 3 states in this little example. Okay, so there's x sub 0, 1, 0, 0. Now, how do we compute x sub 1? So we're going to multiply x sub 0 times p. We'll multiply this vector by this matrix, and that's going to give us 1, 6, 2/3, 1, 6. So now this is our current state after one iteration. And after 2 iterations, we're going to multiply again by x1 by the transition probability matrix P. So we have the current state times the transition probability matrix. And that's going to give us a new distribution over possible states. And if we continue this process from 1, 0, 0 through 1, 6, 2/3, 1, 6, all the way until we reach a steady state, we're going to get a steady state of 5/18, 4/9, 5/18. So that's going to be the long-term visit rate for node 1, node 2, and node 3. And that's going to be the page rank of node 1, the page rank of node 2, and the page rank of node 3. So in summary, for PageRank, in pre-processing, we take the adjacency matrix of the web, the graph of links, and we build our probability matrix P with whatever teleportation probability we like. From that, we compute the PageRank vector, maybe by power iteration. And then pi sub I, the PageRank of page I, is going to give us a number between 0 and 1. So now at query time, we're going to retrieve all the pages that match our query. We're going to rank them by their PageRank, and notice that this ranking is query independent. So PageRank doesn't even look at the query. It's a static fact about the structure of the web. So when we use PageRank in any kind of information retrieval algorithm, we're going to want to combine it with all the other query-specific measures of relevance, all of our TF-IDF and cosines and so on that take the query into account. So PageRank, an important way to compute the relevance of a page, which is an important factor in finding a relevant result for a query.